The big goal of physics is to classify a system so that we can predict what it's going to do at some later time. Take, for example, this pendulum. It's just swinging back and forth, and up top we have a graph of theta versus time, or the angle that this pendulum has over time. And it's easy to tell that this system is very predictable. I'm pretty sure in the future it's just going to keep on going this up and down motion. Now, what if we add some external forces to this pendulum? So this pendulum has a couple forces on it. First of all, there's a damping force added to it. So maybe some friction around the axle or some air drag type of thing. There's also a driving force on this pendulum. So the driving force will go up, and down like this, where at the peaks, it's going to be pushing the pendulum really hard in the positive theta, and at the valleys, it's going to be pushing really hard in the negative. So if you can watch this pendulum, you'll see that every once in a while it slows down and starts going left, and then it slows down and starts going right. So this periodic driving force is also acting on the pendulum. So what we're starting to see here with this pendulum is a little bit of chaotic behavior. In this graph of theta over time, we're not seeing much of a pattern, and it'd be a lot harder to predict what this pendulum is going to do at some future time. Chaos theory in physics is all about trying to find patterns in the chaos of systems like this one. So in this video, I'm going to be going over a few principles of chaos theory, including strange attractors, poincare plots, as well as bifurcation plots. And I took all this information from the Computational Physics second edition by Giordano and Nakanishi, and I decided to code it myself using Python. So quick overview of my code. First of all, I have a class called pendulum. And what this class does is it performs Runge Kutta 2 simulations to calculate the position and velocity of the pendulum at different points in time. So this pendulum has the option for three forces: a periodic driving force, a damping force, and a gravitational force. And that's what causes it to be chaotic, because of all these forces. Then I have a function called run_rk2. And what this does is it takes in a time parameter for how much time you want to run the simulation. And then it runs Runge Kutta 2 until that time is up. So what this function does is, first of all, it gets a list of thetas and omegas, where theta is the angle of the pendulum, omega is the angular velocity. And what it does is every loop until time is up, it's going to make an updated array of the thetas and omegas, and that's going to use the Runge Kutta 2 method. So if you go up here to the Runge Kutta 2 method, what Runge Kutta does is it's a lot like Euler's method, but a little bit more precise. So a quick overview of how Runge Kutta 2 works. We have a list. Let's say our list already has a few thetas in it. Let's say this is time, and this is the next time. So Runge Kutta is trying to find what will theta be at this next time. So what it does is it uses Euler's method to push the forces onto this point to calculate what the point will be there. But then it goes a little bit more precise by going 1/2 step in the future and calculating what the force would look like right there. So let's say it looks like this. Then it pushes that 1/2 step onto the full step, and it finally calculates the next theta to be right there. So how the Runge Kutta 2 function works is K1 is the theta point one time step in the future. So all this is doing is Euler's method one time. Then K2 takes the same thing but only 1/2 a step in the future. And then the updated array that it returns is at one time step in the future, but with the data at 1/2 the step. So a little bit more accurate. And you probably noticed that the function uses the RK2 derivatives method. This one's just right above. It just calculates using Euler's method the next point based on the time. So as you can see here, derivative of theta over time is omega, but then the derivative of omega over time is our acceleration. And that takes into account all the forces, basically. Just like Newton's second law, the sum of the forces is equal to the mass times acceleration. So the first plot we're going to look at here is a theta versus time graph. So theta meaning the angle of the pendulum and then over time. So one thing about chaotic systems is if you change one of the initial conditions just slightly, it could dramatically change how theta changes over time. For example, here is a pendulum with the driving force 1.2. Let's use the same driving force, but we'll change theta initial just a little bit. So instead of 0.2, we'll just do 0.3. Now when we look at this plot, all of a sudden we see a much different graph than before. So that's the thing about chaotic systems. They can be deterministic. We can tell where this pendulum will be in the future. However, if we just change one of the initial conditions, the whole thing will change. One helpful plot to help us understand some pattern in the chaos is called an attractor or a phase space diagram. So this diagram plots omega, which is the angular velocity, versus theta. So over a certain amount of time, we have plotted theta versus omega. And as you can see, it's a little bit crazy, but it follows this shape. So we can see that there's some kind of pattern emerging in the chaos already. Now, something interesting we can do is called a poincare plot. Poincare plots can be helpful to visualize a correlation between two things. So what we're looking at here is the same plot of theta versus omega, but this time only plotting the points where the driving frequency is in phase. In systems that are not chaotic, we only see one point or a small group of points. But in chaotic systems like this one, we see the point moves around throughout the run. A very useful tool in chaos theory would be to calculate when a system starts moving towards chaos. For example, this pendulum has a low driving force of 0.7, and as you can see, it's becoming very periodic and predictable. Now, if I just change this driving force to 1.7, we can see now with a stronger driving force, the graph does not look nearly as predictable as before. So there's got to be a way to calculate when this system starts to become chaotic. To see chaos emerging in a system, we can plot several different graphs of theta versus time. So this one is a graph with the driving force of 1.4. And as you can see here, it looks very periodic. The distance between two of these spikes would be one period of oscillation of the driving frequency. So this graph is basically telling us that the period of oscillation of the pendulum is the same as the driving frequency, and that's at 1.4 driving force. Now let's try a different value of driving force, 1.44 instead of just 1.4. We'll show the same plot of theta versus time, and now we see a pattern again, but it's not quite the same as the driving frequency. It looks like our period of oscillation for a pendulum happens once every 2 periods of the driving frequency. Now we're going to try another value. We're going to try 1.465. This period is 4 times the oscillation of the driving frequency. As you can see, there's one big hump right here, a small one, another big one, and a medium one right here. So the pattern only repeats 1 time every 4 periods of the driving frequency. But our pendulum still has a periodic oscillation. Let's test another value. Let's try 1.7 as our driving force. Now with a value of 1.7, all of a sudden our pendulum has descended into chaos. There's a really helpful graph that we can create to show when the pendulum descends into chaos, and it's called a bifurcation plot. So the bifurcation plot takes quite a while to run. As you can see down here in my outputs, it's taken quite a few minutes, but I'll explain a little bit how it works. Basically what it's doing is it's going to run a simulation with a certain driving force, and then it's going to poincare plot that simulation, meaning only keep the theta points that are in phase with the driving frequency. Then it's going to plot the driving force versus the theta points, and then it's going to move on to the next driving force. And by the end of it, we're going to have a plot of driving force on the x-axis and the theta values on the y-axis. And these, remember, these are only the theta values when the driving frequency was in phase. So here's our completed bifurcation plot. Now, what is this plot even telling us? Well, what this simulation was, we took a driving force, let's say 1.36, and we ran a whole simulation of the pendulum with that driving force. We calculated the thetas, but we only kept the thetas that were in phase with the driving frequency. So basically like a poincare plot for each of these points. Then we plotted all of those thetas on the same vertical column. And so as you can see here at 1.36 all the way up to 1.42, all the thetas were in the same spot. What that means is there's one theta value that is in phase with the driving frequency. So if we look over here to the left on our theta versus time graph, this is for driving frequency 1.35, so around here. And what we see here on the theta versus time graph is that the period of oscillations of the pendulum is equal to the period of oscillations of the driving frequency. And so that's why we only have one dot here on this bifurcation diagram. Around 1.425 in this area, all of a sudden it splits into two values. So what this splitting means is that there was two theta values that were in sync with the driving frequency. And so if we look over here at the theta versus time graph, we can see that there's two periods of the driving frequency for every one period of the theta. And so that's why over here we see two theta values that were in sync. Again, over here to the 1.46 to 1.48 range, we should see 4 periods of the driving frequency for every one period of our pendulum. And if we look over here on the theta versus time graph, we see just that. So this bifurcation diagram shows us how our system descends into chaos. It starts off non-chaotic for all these different driving forces, then all of a sudden it branches out. So it could be one or the other, and then all of a sudden past 1.48, it goes complete chaos. I was curious to see what happens after 1.5. And so I plotted from 1.35 driving force all the way up to 1.7. And here's what happened. We see our bifurcation diagram. Around 1.5, 1.55, it looks completely chaotic. We might have some order here in the middle with 4 thetas, but it's hard to tell. I need to run it again with more precision to know for sure. But then you get over here to the 1.6 range and there's 3 lines, which I found very interesting. It becomes orderly again. And then around 1.7, it goes into chaos again. In conclusion, chaos theory is super interesting. We can find some patterns in the chaotic behavior like this pendulum, and this could apply to a lot of different fields. For example, when I think of a pendulum in physics, I immediately think of a harmonic oscillator, which we see in quantum mechanics, all over particle physics. I'm sure there'd be a lot of chaotic systems to be studied in that field. But chaos theory can have other applications in different fields as well. If there's any chaotic system and we need to find some pattern in there, we can use these tools. So thank you guys for watching. And again, if you guys want to access this project, just head over to my GitHub, my chaotic pendulum repository, and I'll see you guys later.